we're going to practice changing between exponential form and log form. And I just want to show you first that we have done this changing forms with different operations as you've learned your algebra along the way. So here's an example of changing forms. Here's a relationship, 12 minus 3 equals 9, true statement. Okay. Another form that shows the same relationship might be 9 plus 3 equals 12. Okay. So it is a different format, but it still shows the relationship between the 12 and the 3 and the 9. So we can do it with addition and subtraction. We can also change forms when we have multiplication or division. If I start with the equation 20 divided by 5 equals 4, this is showing a relationship between these numbers and division. Right? The same relationship between these numbers can be shown with multiplication. I could say 5 times 4 equals 20. So it's a different form, again, showing the same relationship between these values. So I want you to take that framework and think of that also when we start working with our logs to exponentials. Right? So here is an exponential form. 3 raised to the 4th power equals 81. There is an equivalent log form, right, that still shows this relationship between these values. So to write the log form, we have to identify that what the base is. So our base is 3 here. We're going to say log base 3. We have to know what the result is, right? The result of raising 3 to this power is 81. And logarithmic expressions here are equal to exponents. So there is our log form for this expression. Okay? Log base 3, 81, is the exponent on 3 that results in 81, and that's 4. So that was changing exponent form to log form. We can also change log form to exponent form. When I see log base 1/2, 8, this is representing the exponent on 1/2 that results in 8. Right? And it's telling us here that that exponent is -3. So we're going to identify the base. The base is 1/2. We're going to identify the exponent, which is -3, and the result of that is that argument 8. So showing the same relationship between these three values, just whether it's in the log form or in the exponential form. Let's try another, starting in exponent form. So I identify that the base is 12. We're going to log form here. So let's see, we're going to say log base 12 of, and then we need the result, and that whole log expression equals the exponent. So this is saying the exponent on 12 that results in 12 is 1. And let's try another exponential form to log form. I'm going to identify the base. We have base 10 here. So we're going to call this log base 10. And then the argument of the log function is the result. So there's our 1,000. And the entire log expression equals the exponent. Now, while we're right here with this, excuse me, with this problem, let's talk about this log base 10. Log base 10 is also known as the common log. You'll find this key on your scientific calculators. So if we have a log base 10, it's pretty universal to leave off that base 10. If I just see log 1,000, everyone's going to understand that this means the common log, that means base 10. I would not count it wrong if I saw something like this, log base 10 1,000, but you need to be ready to encounter it in this format also. All right, let's finish off here then. Here's another log form. This is saying if we have a base 5 and we want the result to be 1 over 125, the exponent needs to be -3. So we identify the base, we identify the exponent, and then we get the result. And we're going to see the same thing here. We're going to identify the base is 6. We're going to identify the exponent is over here, and then the result is 1. Now we can pause right here. We have a couple properties using ones and zeros. So let's talk about that for a second. If you have the base here matching the argument, this has to be 1. Right? So we could get fancy, and I could say something like a log base 8.5 of 8.5. Right? This is the exponent on 8.5 that results in 8.5. Well, that exponent has to be 1. Okay? Or we could say log square root 2 of square root 2. This represents the exponent on square root of 2 that results in square root 2. That's got to be 1. So that is something to watch out for. It's really just using the definition, but you'll notice that when we have the exponent of 1. Okay. In this expression, we have an exponent of 0. Right? Well, if we have a positive number raised to the 0 power, we're always going to get 1. So some other examples of this work with 0. I could have any base down here I wanted. I could have log of base 7/5 1. So this is representing the exponent on 7/5 that results in 1. Well, that exponent has to be 0. Okay. Or if I had log base 3.5 of 3.5. Nope, sorry. Log base 3.5 of 1. There we go. That's the pattern we're looking at, where our argument is 1, or the result of raising to the power is 1. So when I see this, I'm thinking, what is the exponent on 3.5 that results in 1? Well, that's got to be 0. Okay. So we'll be ready for more of those logarithms with 1 exponents and 0 exponents when we encounter them. Now let's take a look at, again, just evaluating some logarithms. So here we're going to find the value of each logarithm expression. Okay, so really focusing on the idea that this is an exponent. This is the exponent on the base of 3 that results in 81. Sometimes it's useful to think about this in its exponent form. So what's going on here is we're trying to find the exponent on 3 that results in 81, like this. Well, you could try with your calculator a bit, or if you're okay with your power rules here, I know 3 squared is 9, 3 cubed is 27, and 3 to the 4th is 81. So let's follow this pattern. Again, what we're looking for here is what is the exponent, this whole expression is an exponent, on 3 that results in 1/3. So if you want to think about it in the exponent form, we're going to think, what is the exponent on 3 that results in 1/3? All right, well, our exponent rules say to get the reciprocal of this base, the exponent has to be negative. Let's try example C here. Now, I'm going to take this 0.01, and remember that when we're in decimal form here, that this first place is the 10ths place, and this place is the 100ths place. So 0.01 is the same as 1/100th. So what we have here is log base 10, or a common log, of 1/100. So the result of this, right, we're looking for what's the exponent on 10 that gives you 1/100. If you want to think in the exponent form, here's what's going on. We're looking for the exponent on 10 that gives us this. Okay. To get a fraction, it needs to be negative. And then I hope we can see that you have to have 10 times 10 to get 100. So the result there is negative 2. For example D, we also have to do a little bit of a change here with this argument. When you see square root 6, I want you to rewrite that with a fraction exponent. Right? Square roots can be written as 1/2 exponents. So what we have here is our log base 6 of 6 to the 1/2. Right? This is an exponent. Right? It is the exponent on 6 that results in 6 to the 1/2. Right? If I want to see that in exponent form, here's what I'd be thinking. What is the exponent on 6 that results in 6 to the 1/2? Well, this is just our property we use when we solved exponential equations. If we can get the bases to match, the exponents have to match. So the exponent there is 1/2. We'll continue with a log base e. So here we're looking for the exponent on e that gives us 1. We were just looking at this rule. If I want to think it through and think, well, what does the exponent form look like? I'm looking for the exponent on e that results in 1. Well, that has to be 0. Right? That's our 0 exponent rule. Now, while we're here, let's talk about this format. We know that if we have a base 10, we're going to call this a common log. So I could write log of 1/100. Right? The same as I can write log base 10 of 1/100. It is understood that this is the common log. If we have base e, then this expression can also be written as a natural log. You'll find that key on your calculators also. The natural log is written with an ln. So I could, instead of writing log base e1, could write natural log 1. Either way, same result. Okay? This unwritten base here is that natural base e. Now, number F here, sorry, with the 27, we're going to take this step by step, but this is not one that I would just do mentally. I'd really rely on that. What does the exponent form look like? Right? So our base is 3. We don't know what the power is. That's what we're trying to find. So 3 raised to what power is going to be equivalent to 27 to the 3/2. Now, I need an extra little step here. We did something similar up above, right, where the bases matched, and that one was pretty easy. Right. Well, now I do not have matching bases, but I can do the work to get those bases to match. Right. So we got to do a little side trip here, and we have to think about writing 27 with a base of 3. Right. So just some powers we should be familiar with, right? 3 to the first is 3. 3 squared, that's 9. How about 3 cubed? That's 27. Right. So I can make a replacement. If I ever see 27, I can replace it with 3 cubed. Well, let's come here and let's try that. Instead of 27, we're going to write 3 cubed and raise that to the 3/2 power. Right? So these expressions here are the same. Right, we've just replaced 27 with 3 cubed. And now I'm going to use the power rule for exponents. That rule says when you raise a power to a power, you multiply those exponents. Right? So if I'm going to multiply 3 times 3/2, right, I can write my work out like that, and I get 9/2. So I'm looking for this mystery exponent, and this is 3 to the 9/2. All right, so the exponent on 3 that gives us 27 to the 3/2 is 9/2.